in order to provide you the full understanding of deriving what we have said earlier in the introduction video, alright, we're gonna first introduce you to the beam understanding of the beam bending. Alright, so the beam bending itself, these are all the terms that you may need to understand. So I'll just start off with the normal strain first. Alright, I'll just use this understanding. Alright, we have a unbent beam, so you'll just have a straight beam like this first. Alright, so the distance from the middle, you have this neutral axis, right, at the middle of the beam, and then, sorry, this is NA, the neutral axis. There'll be a distance to the neutral axis. Alright, so this point at the distance is just Y. Just take note of that. Alright, and then your overall basis axis is just X and Y only. Okay, now if you subject your beam to a certain bending, such as this one over here, alright, and then you have a certain triangular shape like this. Okay, then if I were to flip this triangular to this one, because it's the same thing, because if you were to close up, this angle is, this triangular is this one, which is also same as this one. Okay, just to let you know lah. Okay, but the angle is still the same. The angles are all the same. So this is open. I mean, this is not open. This is opposite. This is adjacent. So we know that for tangent, all right, tangent theta is equals to O over A, and therefore theta is equals to tangent inverse O over A. Okay, next, for small angle, very super small angle in terms of radian, alright, your tangent inverse O over A will be equals to O over A. Okay, you can just sub it in. Alright, if you have tangent inverse O over A, for example, is 0.05. If you were to tangent inverse this one, you will get something like 0.049. Okay, in terms of radian, please be careful. Okay, so we have O over A, such of the case. Okay, so far so good, and therefore I can simply say that the relationship to describe theta is equals to O over A now. Alright, because tangent inverse O over A is simply O over A. Okay, so I'll just write theta is equals to O over A, and we know that opposite side is actually the opposite angle to the opposite. The angle is actually the strain, right? So I have a strain divided by your A adjacent, which is your distance to the neutral axis, epsilon y. So theta is equals to epsilon divided by y. So take note, I'm simply just only dealing with the strain. Alright, the strain is going still in the x direction. If you have a beam over here, alright, this is the x direction. If you have a beam like this, as we see, this is still in the x direction. But the whole basis is changing. But just to let you know, we just want to let you know this things, that's all. Okay, we are only talking about the strain. Alright, so we have proved to you that theta is equals to strain over y, and we also know that theta is equals to 1 over r. It's just the radius curvature, that's all. Alright, and therefore, since we know theta is equals to 1 over r, theta is equals to epsilon over y, I just simply put them together like this. Okay, rearrange in terms of the strain, I'll have y over r. Okay, so it's in terms of the y, the distance from the neutral axis from a certain point to, as compared to r, is your strain. Okay, as you can see, it's quite intuitive to you already, right? Because if you were to look at in terms of a bar, alright, this is the original length. You have a certain displacement u, alright, which is like this. So for this case, this is in terms of your strain is equals to u over your original length l. Same thing in our case right here, we are talking about the original length as r, alright, the radius of curvature, and then divided by the y, that is the distance, because the more you bend, the distance y is going to increase in this direction. Alright, take note of this. Alright, so the strain is equals to y over r, and we can say that the strain in the x direction, because you know that the strain we have shown you is into this x direction, so therefore it's just ex. Okay, but this is applicable for when you're bending upwards. if you're bending downwards, alright, let's say you're bending downwards, the distance from the neutral axis is actually going over here, which is minus y. So over here it's going upwards, so it's y. So if it's bending downwards, it's minus y. So in our case, we actually use minus y because we often bend in this direction more. Alright, normally we always bend in this direction, right, Diobo? So we just write in terms of this. And this is the first understanding of our ex equals to y over this one. Alright, so this is your r. So minus y over r. Alright, so this is your strain. Check. I took 5 minutes to explain the strain. Anyway, so now next is that stress is equals to Young modulus times strain, taking that you assume that the material itself is elastic. Alright, so we are talking about elastic region over here. So elastic region, we can use the elastic constitutive equation. Alright, and therefore since we know that our epsilon is this one, Ex, I'll just simply sub in as E. Since we have minus over here, we'll just put minus outside first, and then y over r. The rho is just your radius of curvature r. Okay, so you have sigma x. Okay, that's all. Your normal stress. If you want to visualize your normal stress is simply, if you look at the cross section of your beam, if you are to draw in terms of a 3D beam, this cross section over here, your stress is acting towards, perpendicular to the side. Alright, so if you were to do in 2D, it's like this. Okay, so therefore, this is why we say that it's a normal stress. Alright, normal in the x direction. Strain is also in the x direction. So be careful of this thing. Alright, this is the integration. Right, now next we're gonna introduce you with normal stress with the bending moment. The normal stress with the bending moment is simply the moment, because in terms of moment, so it's equals to force times the perpendicular distance. Alright, and then we know that the force is stress times area, and you know that stress, we know that it's stress x. So it's stress x, and then area we just write as dA. Alright, times perpendicular distance, what is it all about? It's y, it's the neutral axis. If you were to go to visualization, your stress is acting upon your this dA over here, shaded in black now. Alright, and the distance, alright, perpendicular distance is the distance, maybe I should define properly. This is your area, alright, this is your area, or the distance I zoom in is this distance over here to your neutral axis. Alright, so I think the arrow over here they didn't draw properly, but I just want to define to you that it's over here. Alright, this distance, okay, it's perpendicular. Alright, and therefore if I have to rearrange, I'll bring this dA to the behind. I have sigma x, maybe subscript x, y, dA. And you know that when you see dA, you need to integrate the whole system by itself, right? Because you're talking about only one small strip of this dA. Or you can talking about this one piece of this dA. You can also do that because they want to draw easily, so they just write this whole strip as dA. But anyway, you're gonna integrate the whole, all this dA by dA by dA all along the dAs. So you're gonna have the full moment at all of the small little area. So the moment itself is simply this one, which is this one. Alright, when you know that your stress, alright, your stress is you know that your force minus F, I should have said is minus F. So your stress is minus stress minus also. Why is it minus F? Is because you have a beam, alright, that is acting downwards. See, you have a force acting downwards, it's going the negative side. Alright, and therefore this is something that you need to understand also. Please be mindful. Look at the force, which direction. You also influence how your moment would be. Alright, in terms of the equation. Please be careful of this thing. Alright. Next we know, so therefore now you know there's normal strain, it's just strain, stress, and then we talk about the moment. Now we're going to talk about the moment curvature relationship. What is it all about? Alright. From here is a little bit abstract, alright, but it's just let's just come here. We know that this thing over here I think is very familiar to use, like macam only. So therefore I'll take this thing, put it over here. Take this thing, I put it over here. Right, so I have mi equals to e over r. I just bring this I upwards, I have m equals to ei over r. Right? I think you're just rearranging stuff. Okay? And this is just what it's talking about. So it's just m equals to ei over r. Okay? So your moment in relation to the curvature, this is 1 over r, right? Your curvature, which means that your theta, your degree of angle, if you remember, theta is equals to 1 over r, or you can just say that is the meaning of that lah. Okay, it's just the arc length itself. Okay, so it's the arc length over here. If I didn't explicitly define, 1 over the radius, alright, is your arc length. Okay, sorry if I didn't actually say that. Okay, but anyway, let's continue. Alright, so the relationship between your arc length and the moment equation, things like that, is all this thing that I've just shown you. Alright, and your arc length itself is in terms of a d2y dx square curvature, because if you were to look at it properly, alright, your curvature of your beam in bending is this, it's going like this, it's like a quadratic. Alright, I will not prove to you how, but the theta is equals to dy over dx. Okay, I also don't know where is it coming from. Alright, but anyway, you know that the curvature is just a second order system, that's all. I'll not go into details because I don't think it's necessary for me in this moment. If in the future you need, I'll just link this to another video. But anyway, your curvature will be in terms of d2y dx square. Okay, that's all. So it's just a relationship between your moment and your radius curvature. So your moment is equals to your radius curvature. That's all. Okay, with relevance to your Young modulus and the second moment of area. Alright, in terms of how the cross-sectional beam of it is, or the whole length is this. Just let you know, right? And then the last one is your fracture formula. Is the one that you often being used. Is talking about your bending stress. Alright, same thing. I take this over here. I bring this I upwards. Sorry, I bring this y upwards. Sorry. So I have 1i over equals to sigma. Alright, so this is your bending stress. So it's this case over here. And then it is minus is because I don't know. Maybe it's your moment is going in this direction, it's minus. If it's going in this direction, it's plus. Alright, it's just the sign language only. Alright. And then nonetheless your second moment of area is still this one. Okay? So therefore I hope that this allows you to visualize your whole bending system in a more clearer way. So in the later parts, I'll not go into that, maybe a little, but at least you get a full clear view of this. Alright, I'll see you soon.